This video is about two things that can't be done with standard Arduino interfaces on an ATtiny. First, we'll see how to generate a periodic interrupt, and then we'll see how to program interrupts directly, allowing much greater efficiency, but coming at the cost of portability and needing care not to conflict with other Arduino features. We'll use the periodic interrupt to implement the switch debouncing algorithm that Jack Gansel described after many measurements and experiments. Debouncing a switch properly is harder than one might think. Most microcontrollers have several hardware timer blocks. Here they are on a Series 1 ATtiny. Arduino uses one or more of them to implement features such as the millis and micros APIs, and also features like tone generation and even pulse width modulation. But different microcontrollers implement different timers, so Arduino provides very abstracted and rather limited access to them. Doing more with timers requires either libraries that provide further abstractions, or code that is specific to particular microcontrollers, that is, code that won't be portable. We'll show non-portable code today. We will use the timer called the Real Time Counter, or RTC. But we need only parts of the RTC block. We'll use the clock selector to choose a clock generated by an internal 32.768 kHz oscillator. We'll leave the 15-bit prescaler in its default state, which leaves the 32.768 kHz clock unchanged. The periodic interrupt timer, or PIT, counts driven by that 32.768 kHz clock and generates an interrupt after every n clocks. We can choose n. All this is controlled by a handful of registers. This one controls the number of cycles between interrupts and also contains an enable bit. We'll write a 5 to the period field and a 1 to the PIT enable field to start the timer and set it to generate an interrupt every 1.95 milliseconds. For other registers, let's look at the software, where we will also see the PIT interrupt handler programmed as a direct interrupt. You may be surprised at how simple this is. But first, here's a system diagram. We have the 7-segment LED display connected to the ATtiny 412 pins PA3 and PA2, as we saw in previous videos. PA1 is an input that reads the switch state. PA6 acts as a pin interrupt, like we saw in my last video. PA7 is an output pin that software can toggle. The ADALM2000 acts as a signal generator. It puts a square wave onto PA6, which causes interrupts. It also acts as an oscilloscope, allowing us to view the toggling pin and the switch. And here's a look at the system on the breadboard. You can see the switch, which I'll press, and the 7-segment display, which will count the switch presses. And here's the software. You can see we're using the 7-segment LED display like we used in some previous videos. And here we're setting some pins or allocating some pins. So PA1 will be an input pin that samples the switch state. And PA7 is an output pin that software can toggle so that we can see activity on the oscilloscope. And then PA6 we're going to configure as a direct pin interrupt, so an external interrupt, and we'll use it to measure performance. And so we want to focus on the direct interrupts. So I'm going to go down to Setup. And well, the first thing we have to do is to set the mode of our input and output pins. So that's done here. And then in order to do direct interrupts, you have to manipulate registers of the interrupting peripheral directly. So first, here's some registers inside the RTC to enable the PIT interrupts. So clock cell is an RTC register, and we're setting it to select the clock, which is from an internal 32.768 kHz oscillator. So that's where we get the clock. And next we have to enable the PIT interrupt. So PIT int control is another register inside the RTC, and so this enables the interrupt. And then next, we have to select the period and enable the PIT. And this is the PIT control A register that we saw previously in the slide. So here we're selecting an interrupt every 64 cycles and enabling the PIT. And so that's what you need to do to enable a periodic interrupt from the PIT. Not too much to it. Now we're also doing that external interrupt. The external interrupt is a port interrupt, in particular port A on this ATtiny 412. And so here, we're using pin 6 as the interrupt pin. So pin 6 control is a control register belonging to port A. And so we enable the interrupt on the rising edge just by setting that single register. And that's all we need to do. except interrupts need interrupt handlers. And so now let's go up and see how those are declared. And so here is the interrupt handler for the pit interrupt. And right here, you have to use this notation. So you say ISR and then the source of the interrupt. And you can see those in the megatinycore documentation at this link here, which I'll try to remember to put below as well. But anyway, so this is the handler for the pit. And the one thing that it absolutely has to do is clear the pit interrupt flag. Otherwise, the interrupt will just go on and on and on. So that's the one thing you have to do. Everything else is the software processing that I'm choosing to do inside the pit interrupt vector. And so this is toggling our toggle pin because we do have pit int defined right now. That's up here. So these define choices determine where in the software the toggle pin gets toggled. And then this is the algorithm for the debouncing of the switch. And I'll go through that in a little more detail later. For now, we'll ignore that. Now, the other direct interrupt is the port A interrupt for pin 6. And the one thing that it absolutely has to do is clear the interrupt flag. So this is pin 6, so that's a mask of 40. So that's what you have to write to port A int flags being another port A register. And then here, if IRQ int is defined, we would toggle the output interrupt pin. But this isn't defined. It's the pit interrupt is defined. So if we run this program, we'd expect to see the toggle pin toggling at basically half the rate at which interrupts are being generated. So let's see that. So we'll build and run, which will just take a minute because this is a small program. And I guess I'll go up here and we can see how big the program is. So pretty small, 1394 bytes of flash and only 19 bytes of SRAM. And so now let's get this out of the way as best we can and run the oscilloscope. So I'll just click on run here and we can see that there's a signal and that the period of the signal is 3.8 something milliseconds, which we expect to be twice the period of our interrupt. So it's working. The pit is generating an interrupt every 1.95 milliseconds. And so that's great. Now let's go back here and make the software bigger again. And let's change this. So we'll define IRQ int, whoops, and get rid of that. And so now the external interrupt is the one that's going to do the toggling. So the port A pin. So we'll run. So it's compiling. Now it's loading. You'll see. All right, that's done. So we'll get this out of the way. Get this out of the way. And you can see the interrupt has stopped. And well, that's because the pit is no longer producing an interrupt and the external interrupt won't fire unless the signal generator generates a signal to cause the external interrupt to interrupt. So we'll go to the signal generator and let's tell it to run at, I don't know, 2 kilohertz, whatever, doesn't matter. And then we'll go back to the oscilloscope and now we see a signal. Yes, now we see a signal and it is at being measured as 1 kilohertz. And that is half of our frequency. So that makes sense. So now let's see if we can make this go a lot faster. And I'm going to bump it all the way up to 500 kilohertz. So that's 500,000 interrupts per second. And so if the toggling is toggling at half that rate, we know this is working. So we have to adjust this to be much tighter on time. And there's our signal. And we can see that it's toggling at about 250 kilohertz, which means that this 500,000 interrupts per second is working. And that's a much higher rate than we were able to generate with the standard Arduino APIs. So that's the advantage of direct interrupts. The problem is you have to be careful how you use them because they interact with other things. Let's go back to the software for a second. I'll pull that out. And so look at here, this interrupt handler here. This interrupt handler would fire for any interrupt pin on port A. So more proper software would check the flags to see which ones are set, which one caused the interrupt. But I'm just assuming that no other interrupt is happening on port A. And I happen to know that to be true. But you have to know how other Arduino features work to make sure that your assumptions are correct. knowing that isn't that easy. You can read the documentation on the megatinycore website, and sometimes you have to read the megatinycore code itself to be sure. But there's quite a bit of documentation on interrupts, so you can take a look at it. Let's return to switch debouncing. So now I've defined SW pressed, which means that the pin will toggle when a switch press is actually detected. Let's scroll down to the pit interrupt vector and remember that this is the code that does the switch debounce detection. I won't spend too much time describing this algorithm. Instead, I'll put a link to Jack Gansel's work below. But in a nutshell, it samples the switch periodically, so for us, once per pit interrupt. It shifts the samples into a state variable and looks for a state in which the most recent high sample is captured followed by the desired number of low samples. This ensures that the switch is in a stable low state. The upper bits in constant 0xe000 act as don't care bits. Set more upper bits to 1 in the constants if you are content to declare that the button has been pressed after sampling fewer consecutive low states. When the press state is detected, we increment a volatile counter that the main loop can read. Now let's scroll down to the main loop, and we can see that if we detect that the button counter has changed, so it's not equal to the old button counter, we set old button counter to button counter and display the new count. So that's how this works. Let's see it in action. Let's build the software. So I'll click that button there, and it'll start compiling. And that's complete. Now it starts to flash. And that's complete. So let me move the software window out of the way, and we should be able to see the oscilloscope and also a camera display of the board. So when I press a button, the scope will trigger on the falling edge of the switch itself. That's the orange trace. And we should be able to see some bouncing, and also we can see the toggle response. So I'll press it once, and we see some bouncing and the toggle response. So let's measure the time it took to recognize the switch was pressed. So I'll use the cursors starting from here, the first trigger point, to here, and we see that it took about 22 milliseconds. That's in line with our algorithm, the number of bits that have to get shifted until the state is detected, like we talked about above. I'll press the button a few more times, and you can see that the counting is reliable. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And you could also see how much variation there is in the bouncing that occurs. So anyway, that's an example of Jack Gansel's switch debouncing algorithm. Returning to performance for just a moment before we end, my previous video, linked below, showed 2 external pin interrupts using the standard Arduino attachInterrupt API. It achieved about 96,000 interrupts per second total on an ATtiny 3224. I decided to change that program to use direct interrupts for an apples-to-apples comparison. You can see it running with 2 times 175,000 or 350,000 interrupts per second. That's a direct comparison between standard and direct interrupts on the ATtiny. You can see the interrupt handler on the left checking both pin interrupts. We've seen how to use direct interrupts rather than the standard Arduino API attachInterrupt. And we see that direct interrupts are much more efficient. We also saw a simple way to generate periodic interrupts and use them to implement a robust switch debouncer. That's enough for today. I'll end this video here. Thanks for watching.